Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to the discussion of the principles and chemical applications of thermodynamics, and today we are going to talk about equilibrium in simple mixtures where there is no chemical reaction. And in this topic we are going to extend our discussion on the concept of chemical potential yet again. Now, when we talk about simple non-reacting mixture, we have seen that the fundamental equation for any such system is given in terms of dG at a given temperature and pressure and the number of different components present in the mixture that is going to be dependent on dt, dp and dni. And corresponding to every such independent fluctuation, I have the coefficients appearing here as S, minus S, plus V and plus mu I. Now, we have already talked about in this course about how to estimate the chemical potential of the ith component in a mixture of capital M ideal gases. So basically the idea is I am looking at the properties of a mixture of M ideal gases and the mixture behaves ideally. And in this case we have been able to show that if Xi is the mole fraction of the ith component in the mixture, and if it is held at a given temperature T and a constant total pressure P, then mu I, that is the chemical potential of the ith component in the mixture at this temperature and total pressure P, will be given by mu I star Tp plus RT ln Xi. So what is mu I star? Mu I star is the chemical potential of the ith component had it been present as a pure substance at the same temperature T and the same pressure P. And now I also know that if I assume an ideal behavior of the gas, in that case the mu I star, that is the chemical potential of the ith component in its pure phase, is given by mu I naught plus RT ln P by P naught. We have already seen that mu I naught is the standard chemical potential at the temperature T, and this corresponds to the standard pressure equal to 1.0 bar. And here I see that because of the presence of the system, the ith component in its pure phase at some other pressure P which is different from the standard pressure, therefore I have this additional contribution coming into the picture. And as you understand then, if I know the given values of temperature and pressure, and also if I know mu I naught and Xi in the mixture, I should be able to estimate mu I Tp. But once again, evaluation of the chemical potential is usually not experimentally accessible. And therefore, what you do is you try to replace the chemical potential and you try to obtain the corresponding quantity in terms of the concentration, for example, in terms of mole fractions. So, for this purpose, one may use the Gibbs-Duhem relations, about which we have talked earlier. And if I use the Gibbs-Duhem relations in conjunction with the expressions given here, it is possible to show that the Gibbs free energy of mixing of capital M ideal gases at a given temperature T and a constant pressure P is given by nRT and then summation over all components I xi ln xi. Now what is N? N is the sum of all the individual components, the number of moles of all the individual components present in the system. And if this is an ideal gas mixture, then the corresponding enthalpy of mixing is going to be equal to 0 and the entropy of mixing is going to be given by an expression like this. Now please remember, in all these cases, in the entire derivation, we have used the understanding that mu I of the ith component in the pure phase is given by a form like this, and mu I in the chemical mixture is given by a form which involves this term RT ln xi over and above the value of chemical potential of the ith component in its pure phase. Now, if I want to extend my discussion to estimation of the chemical potential in a liquid mixture, the basic question that I would be asking is, how does the Gibbs free energy of a liquid vary with composition? And in order to address this question properly, let me take a simple example where I have a binary liquid mixture and I will be representing the solvent in this binary mixture as A and the solute as B. So by definition, I have a small amount of the solute B dissolved in a large excess of the solvent A. Now this is a typical representation of the situation that I have in mind. I have the liquid mixture A plus B both in the liquid phase, and I understand that in a sealed vessel this liquid will be coexisting in equilibrium with the vapor phase, and both the liquid and the vapor phase have A and B as their constituents. And here let me introduce certain notations. I would assume that the vapor pressure of the pure liquid A is PA star and the vapor of A behaves ideally. Now with this notation in mind, what I can say is this: if the liquid mixture is in equilibrium with the mixture in its vapor phase, then if I concentrate on the component A in this case, then I must be having at equilibrium the chemical potential of the component A having the same value irrespective of whether it is present in the liquid phase or in the gas phase. Or in other words, I can write that mu A in the gas phase must be equal to mu B in the liquid phase. You must realize that I am talking about this equilibrium at a given temperature and pressure. And I'm talking about a situation where, unlike the previous examples that I have taken, I now have a mixture that can coexist in equilibrium both in the liquid as well as in the vapor phase. Now, I understand that mu A in the gas phase, which I represent using a blue color, that can be written as mu A naught plus RT ln PA by P naught. Now, why do you think I can write this expression like this? This is simply because I have assumed that the vapor of A behaves ideally. And therefore, here I am assuming that PA is the partial pressure of the component A in the vapor mixture A plus B. And what is P naught? P naught is the standard pressure of 1.0 bar. Now, if I think about the pure phase of A, where the pure liquid is in contact with its vapor phase, then I understand that mu A star is going to be equal to mu A naught plus RT ln PA star by P naught. Here I am using the notation star to represent the situation where the pure substance A has its liquid and vapor phase in equilibrium with each other at a given temperature T and some given total pressure PA star. Okay. Now, if I combine these two equations and I eliminate mu A naught from both the equations, then what I have is this particular expression. I have the chemical potential of the component A in the vapor phase that is equal to chemical potential of the pure liquid A mu A star plus RT ln PA by PA star. Now, this equation is going to tell me that I can use this expression in conjunction with some other equation that is known in the literature. And this is the famous Raoult's law. Now, what is the Raoult's law? The Raoult's law says that let PA star be the vapor pressure of the pure liquid A. Now, if I dissolve a solute in A, then once again there will be a vapor in equilibrium with the liquid solution. Let PA be the partial pressure of the component A in contact with the liquid solution A plus B. And the Raoult's law, by collating a very large number of experiments, found that the partial pressure of A in the vapor in equilibrium with the solution, that is given by XA into PA star. Therefore, please try to remember that when I am talking about PA star, I have only the component A in its pure phase, and here I have the pure component A in the vapor phase. And under such condition, if I think about this pure phase at the same temperature T, then PA star is the vapor pressure of the pure liquid A. And what I am talking about here is PA, which is the partial vapor pressure of A under such situation. And Raoult's law tells me that PA must be equal to XA into PA star, where XA is the mole fraction of the liquid A in the component A in the liquid phase. Now, if I combine this expression with the Raoult's law, what should I get? What should I get is as follows. I get mu A, that is the chemical potential of the component A in the vapor phase in a situation like this, that is equal to mu A star plus RT ln XA. So that says that if I know the mole fraction of the solvent A in the solution, in that case, I should be able to find out the chemical potential of the component A in the vapor phase, which is in equilibrium with the liquid solution. Now, once you understand this, then I also understand that there are several other chemical experiments where it has been found that the Raoult's law is not valid. So in that case, what one uses is what is known as the Henry's law. Now, Henry's law will be applicable for real solutions at low concentrations. Now, let me remind you that in the case of application of Raoult's law, this expression of mu is assumed to be the defining expression for an ideal solution. So, if a liquid solution obeys the Raoult's law, it is called an ideal solution. And here we are saying that in an ideal solution, the chemical potential of A in the vapor phase must be equal to mu A star plus RT ln XA. And this is also taken to be a definition of an ideal solution. On the other hand, when I talk about real solutions at low concentrations, it is also found that the partial pressure of the solute B in the vapor phase that I see in equilibrium with the liquid solution, that is proportional to the mole fraction of the solute Xb. And here Kb is the Henry's law constant. It has units of pressure, but you must realize that unlike the case of the solvent A, this is not the partial pressure of pure B. And under such circumstances, you use this equation representing the Henry's law as a defining expression for what is known as an ideal dilute solution. So what is an ideal dilute solution? An ideal dilute solution is a liquid mixture for which the solute obeys the Henry's law and the solvent obeys the Raoult's law. Now, how does this situation vary from the previous situation of the ideal solution? In an ideal solution, we have a liquid mixture for which both the solute and the solvent obey Raoult's law. But if I have an ideal dilute solution, I have a liquid mixture for which the solvent still obeys Raoult's law, but the solute now obeys Henry's law. Later on, when we talk about the applications of these thermodynamic principles in realistic chemical mixtures, we will take examples of what an ideal solution and what an ideal dilute solution correspond to. But at this stage, let me take these definitions forward and try and talk about the thermodynamics of mixing of two liquids to form an ideal solution. So this is the experimental situation that I have in hand. Now I have the pure liquid A and I also have the pure liquid B, which are separated from each other before mixing and maintained at the same temperature T. Now, if I allow them to mix, and upon mixing they form an ideal solution at the same temperature T, then I have this ideal solution A plus B. Then I can say that before mixing, the Gibbs free energy of the system in the initial state, that is G initial, that must be given by Na mu A star plus Nb mu B star. So once again, I am assuming that before mixing, I had Na moles of the pure liquid A at a temperature T such that its chemical potential is mu A star. Similarly, I have assumed that I had Nb moles of the pure liquid B at a temperature T such that its chemical potential before mixing was mu B star. Now, after mixing, the final Gibbs free energy would once again be given by Na mu A plus Nb mu B. Now, what is the component mu A? That is the chemical potential of the component A in the ideal solution A plus B at a temperature T. Similarly, we have mu B as the chemical potential of the component B in the ideal solution at temperature T. Now you understand that the reason why I could write these expressions for G initial and G final is that I'm using the Gibbs-Duhem relationship. And now, knowing how to relate the chemical potential of the ith component of the ideal solution, I know that mu I must be equal to mu I star plus RT ln xi for each of the components A and B in this binary ideal solution. Therefore, if I rewrite the G final, then I will be replacing mu A and mu B by these expressions for each of them. So G final now is Na into this expression for mu A plus Nb into this expression for mu B. Now I realize that G final, the first term that appears here is Na mu A star plus Nb mu B star. And these two terms combine to give me G initial. And therefore, the Gibbs free energy of mixing can be very quickly shown to be nRT into Xa ln Xa plus Xb ln Xb, where I have used the definition small n is the total number of moles of A and B present in the mixture, and small n is Na plus Nb. Now, I can very quickly then show that the entropy of mixing under such condition is minus Nr Xa ln Xa plus Xb ln Xb. Now, as you see that here comes the beauty of the treatment that we are doing in terms of chemical potential. I have been using this expression that in this ideal solution, I have mu I given by mu I star plus RT ln Xi. And this expression I have used to be valid even when I'm talking about mixing of two liquids. This we have seen to be valid while we talked about mixing of two ideal gases. And therefore, as you understand that as long as I can use an expression like this for the chemical potential in the mixture, I will always be having a delta G mixing. That is the Gibbs free energy of mixing, which has this general form that it is nRT into XA ln XA plus XB ln XB. And this gives a powerful simplification to the entire exercise where we are talking about thermodynamics of mixing, irrespective of whether we are talking about an ideal gas mixture of A and B or an ideal solution formed by A and B. Now, this also brings us to some very important properties of a solution, and these are known as the colligative properties. Now, when I talk about a colligative property of a solution, I am essentially talking about those properties of the solution that depends only on the number of solute particles present in the solution, and the property should not depend on the identity of the solute. And the thermodynamic basis of such colligative properties can be understood by looking at this picture which we have seen earlier. So what I am doing here is I am plotting the temperature along the x-axis, I am plotting the chemical potential along the y-axis, and if I have the pure phase of A, that is the solvent in my solution, then I have this is the variation of mu for the solid A. This is the variation of mu for the pure liquid A, and this is the variation of the pure gas A. Now I understand that if I want to talk about the solution, I need to understand what happens when I dissolve the solute B in liquid A. Now I understand that when I have the solution, mu A would be given by mu A star plus RT ln XA. Now XA is less than 1 in the solution, therefore RT ln XA must be less than 0. Therefore, I must be having mu A less than mu A star at a given temperature in solution, and therefore I conclude that the chemical potential of A in solution decreases compared to its value in the pure phase. And now in this picture, if I think about any given temperature like this, if I dissolve a solute in A, I expect its value, the value of its chemical potential to be somewhere here. Similarly, if I have some other temperature like this is where its chemical potential would be located. This tells us that if I plot the chemical potential of the solution as a function of temperature, this is the curve that will give me the variation of the chemical potential of the component A when it is present in the solution. Now, what is the indication from this particular plot? I understand that earlier the solid curve and the liquid curve intersected at this point, and the corresponding temperature at 1 atmospheric pressure is given by the freezing temperature of the pure liquid A. Now, when I have a solute dissolved in the liquid, I find that the solid A would be in equilibrium with the solution at a new temperature Tf prime. And therefore, what I am looking at, because of the presence of the solute in solution, is that Tf is now shifted to a lower value Tf prime. And this is the well-known colligative property which is known as the depression of freezing point. As you see that in the pure solvent, A, the liquid gas coexistence temperature was located here, and therefore the boiling point of the pure liquid was this temperature Tb at 1 atmospheric pressure. Now, if you have in the liquid phase the solution of B in A, then you understand that now the new equilibrium temperature is going to be Tb prime, which indicates that I will have an elevation of boiling point. And therefore, the thermodynamics of solutions require us to give a basis, a quantitative basis of the colligative properties in terms of chemical potential. So in conclusion, I would like to say that we have been able to show that if I have an ideal solution, in that case, it is possible to find out the chemical potential of the component A or the component B, depending on the different situations that you have in that solution, and that we observe colligative properties of these solutions follow directly from the dependence of the chemical potential of component A, whether it is present in the pure phase or in the solution. Thank you.